Maybe a little logistics. So we have to cover number 4, which is mining with events and tickets, and also conclusions. So maybe we'll be able to cover 4 before the break, right? And then we'll come back after with a conclusion, which is not big portion, but that's where we can talk about where we are now, state of the art, where are we going, what the industrial issues, or what the issues that industry sees, and essentially how the data mining that we have here can apply. So maybe that's the right thing to do. Does this has a pointer? I don't know. Let's see. Okay, then no. Okay. What we talked about before in this talk, you already heard about the logs, mining logs, and then mining events, which is essentially similar, the different form of the log data, the events. So now the next step, we also at the beginning look at the essentially the first picture and said, well, what happens, how monitoring affects, or what monitoring does, it tries to prevent or notify somebody, either a system or a person, about upcoming issue, and therefore monitors sometimes set up very generous. But the goal is to be able to set them up correctly, to understand where the data, where the differences are, and actually to be able finally to understand the issue which monitor is trying to identify or trying to signal about, and to resolve the issues automatically, right? And so what we found that events and logs are they are connected to the tickets, and the data in the ticket overall is very helpful, or could be very helpful. So how is it helpful, and what are we doing with the tickets? So 2 types of tickets, right? It was mentioned before, monitoring ticket and manual ticket. Monitoring comes from the system. There is a description generated by the machine, which is great because there is a pattern, there is enough information. There is a resolution in the monitoring ticket, not generated by the machine today, most likely by a person, which means it has all issues that you will see in the text that person enter, right? Not enough information, or information entered in different, there is abbreviations and so on. And then we have manual tickets. And manual tickets have all aspects of monitoring ticket except the description of the problem, again, entered manually, meaning not completely described maybe, the language sometimes, there is a mixture of languages, and all the issues that I'm sure you've seen in other areas too. So still, we want to use the ticket data in order to classify the problem. Why do we need to classify? The notion is, if we're able to group our historical tickets that have resolution in them nicely, and then we have incoming ticket, and we kind of say, oh, this incoming ticket actually fits into this particular category or matches this category, now all of a sudden I have an idea how to resolve it, right? At least I can recommend a person to look at the tickets from the same category. So classification were done and being done, it always somehow comes to classification problem, right? Or we like to get it to classification problem. This is a type of classification that we looked at. It was actually hierarchical classification. And you can see this is different. Again, there is a lot of related work in this particular area in terms of classification algorithms. What we're looking at, hierarchical classification. What it helps and how it helps us. It helps us by, first of all, the result of classification itself is better because we now can discard those nodes which don't have a right connection to a parent node, right? So given the ticket, node is positive, could be positive only if its parent is positive. Additional restriction results are better. And you can see that here, again, the classification, multi-label classification, could be restricted. You can have multiple paths and you can have single paths. When we do classification, we can see 4 different use cases. So we consider 4 different use cases. This is error, in your typical type 1 error, false negative, type 2 error, false positive. And what we're trying, what we're doing, we're combining or creating a loss function. And we combine in this loss function different possibilities of how we can misclassify. And of course, and you can see what's used here, right? What different, different loss went into this function. And the goal is, of course, minimize loss. So here, in order to minimize loss, we need to, this is loss overall, as described right here. I don't know how to use it, but that's okay. And you can see that, again, the complexity potentially large, right? So what to do here? The proposal was, or one of the things that we looked at, actually look at an equivalent deviation. And that allows us to do a little bit better. We can reduce it to computing different probabilities. And we can use here the binary, you can see the probability y by yix as a binary classifier on node I. So that's the approach. Of course, there are a number of other works or publications that people work on it. There are different ones. So most of them are actually supervised, right? And that's always a problem. Actually, maybe when we talk about the future work, one of the problems is that we have limited number of labeled data, and we have very limited number of people who can help or who can do this supervised, help with supervised work. And so, but this one is actually capable of doing the work automatically. So that was work when I kind of skipped result, don't show result here, but of the approach was was much better than if we, in comparison to multi-label and classification, just straightforward without hierarchical, ensuring hierarchical structure after post-processing. And so in addition to that, we also still take in consideration that there are people who have information which is not recorded anywhere, and therefore we can talk with these people, and the people can provide us feedback on the classification that we built. And if we consider this feedback that we get from people, then obviously we get better results, right? So you can see here that incorporating the knowledge essentially provides better results. So assuming now that we can classify with very good precision and good coverage, so when I say good precision and good coverage, sort of think about it from two aspects. One, state of the art. Another one, industry. Industry is different because if state of the art is 70% great success, for industry it means errors 30%. Potentially, third of issues would be misclassified, and we need to do something about it, right? And this third of issues could be a lot of time spent on empty cycles. So that's where the, in particular, ticket resolution recommendation, that's where it comes to. If I misclassify the ticket and send it to a wrong person, this person will spend time, need to find who to send it to, who is the right person, and that's all. Meanwhile, problem exists, right? So that's really not a good issue. So the precision of recommendation needs to be very, very good, right? Or recommendation needs to be very precise. And as we go forward, but now we started to look at there are some tickets that does not require a lot of brain power, and they are repetitive, so we need to automate it. So now when we talk about automating, we're actually getting to all new level of requirements. Now you sending it not to a person who can say, look at saying, well, this recommendation not clear, on this recommendation not very good. Now you're sending it to the machine that probably doesn't have this capacity, most likely, right? Anyway, so we're talking about ticket recommendations. So what you see here, results of the simple data analysis: 3 large accounts, huge number of tickets, different time frame, and you can see that many tickets are actually repeating, repeating issues. And you can see that resolutions, the number of resolutions much smaller, which essentially means that the same issue occurring often, and then the resolution is the same. If you look at the next one, this graph, what here it tells me that luckily there is a large number of large number of tickets with similar resolutions, and it has a long tail, right? So probably we never get to the point where we're automating everything 100%. But maybe because of this graph, I have a hope that we can automate, I don't know, a large portion of it, say 60. This is the same picture that Dr. Lee went through, right? This is a picture that talks about how the whole life cycle of the event and ticket, where it ends. And this is, we talk about similar tickets. So related work to this area, user-based recommendation algorithms, item-based recommendation algorithms, constraint-based recommender system, multiple objective optimization. Recommendation is very well researched and very attractive area, right? Because recommendation is not only in the system as we work with here, but any recommendation. Is it advertising? That's essentially a recommendation too. However, if we look at our tickets, they present some challenges. We started with the top K recommendation. How is that moving? With top K recommendation for classifying the tickets, and it provided us some good results. But not maybe again, what we're trying to do, we're trying to classify, and we're trying to understand how incoming tickets that generated by monitoring actually similar to class that we defined, right? Or the tickets in a particular group as we defined. So ticket has metadata, we call categorical data, and we also have a ticket has description and resolution, which is textual data. And so how are we using both of them, a categorical data and textual data, in order to define similarity and how we map then incoming ticket into it? So first started with description. The idea is simple. This event or this ticket which is coming in needs to look very similar that description of the ticket from the past, right? And we do some training and we get some good results, somewhat good results, right? And I'll show the ticket so you'll see why. But then results may be not that good. So because also keep in mind, we're talking about monitoring being set up by different people. Template of monitoring that Tao Li was talking about before was developed by different people. It's coming from different accounts, different customers, so just simply different machines that different people are responsible for. So actually just matching the description, working with description doesn't give us best results. What gives us best results when we start looking at the resolutions too. So now we have, when we work with historical ticket, we'll look at all information which is in the ticket. and it gives us better classification. And furthermore, we apply metric learning for the understanding the similarity, build it in the similarity, and we get, you can see, get even better results. Okay, so you can see some of how it was implemented, right? We have an objective function that we define, and this is we need to minimize the function, and you can see that this projection matrix for similarity. We have topic level feature extraction, and finally manually categorized label. So that gave us a little bit more, a little bit better results, right? Gave us a step forward, a little bit better step forward. We still now, our ambitions, of course, grew, right? We want to do more. We want to automate resolution as much as possible, to the point that today we provide recommendation to a person, and person looks at it and says, yes, no, let me do that. Tomorrow, we want to actually reverse it a little bit, and what we want to create recommendation to a machine. Machine will try to execute or react on our recommendation, and if it doesn't work, if it's for whatever reason we didn't get the right results, we send it to a person. So the game changed, and even though it's maybe not, the players are all the same, but changing the process defined for us requirement for completely different level of precision and potentially coverage, right? So that's where we're going. And so what we figure out was looking just, we need to create a knowledge base, right? There is a knowledge that exists somewhere in person and people mind. There is knowledge that exists in so many different sources. It is data online. It is a online manuals. It is chat discussions or online. It is, you name it. So we get to the point where we need actually to create the data sources. Again, creating data sources, and we start with a ticket. What is a challenge there? Unstructured text, I talk about challenge a little bit, and I think everybody who works with the text understands it very well. Now, structured text, there are some interesting challenges that were presented that we kind of didn't anticipate before until we start looking at it. For example, sometimes unstructured text set just randomly or based on the fact, it's all set by people. So if I am in a rush and there is 220 entries in the list, I don't have time to go through that. Let me put the first one, right? Surprisingly, but when we look at the percentage of categorical data, we see that very often the first entry in the long list is chosen, right? Which means we cannot completely trust the data. So that provides additional challenge for us. And you can see here, this is some examples of why you cannot trust, right? Well, what you essentially, you see there is on the second graph here, this one. What it says here, that this particular component for the failure identified as unknown. It may be in some cases unknown, rare cases, but most likely once ticket resolved, everybody knows where the problem was, right? Or at least, maybe not what the problem was, but at least you were able to localize it. So goes back to the fact that we not necessarily can trust the data. So we need to be able to extract knowledge and to create the knowledge base. So here, these three steps that we set up to do, we went through. Phrase extraction step stage, there is knowledge construction stage, and the ticket resolution stage. And so very quickly, unfortunately, but For extraction stage, we use information, or we use known algorithm to extract data. And now if I'll go here, you can see what we do. We extract phrases, and the phrases come with the frequencies. And the way it is done, you look at the word and you see how often word appears in your corpus of data, and then you see what the next word appears to this word. And so now you have a two word, and you look a two word phrase, and so on and so on. So you extract different phrases, and that's how you're able to get the content without actually original dictionary. So that becomes your dictionary. And then after this extraction, we do phrase refining, which is with some known, some known algorithms, methods here. And then we construct this knowledge, right? In this case, the schema created manually, or the ontology created manually, and then it's populated. So finally, we're looking at the ticket resolution state when we get the incoming ticket, we tokenize it, we try to match it to the knowledge that we already have, right? And as I go through that, hopefully you can see some information, and you can see how it's done. This is example. Maybe that's what I leave you with, and then we'll come back with conclusion and interesting problems, or next step problems for after the coffee. This is two tickets which describe the same issue. You can see that neither words are the same, nor amount of words, but they actually describe the same issue. And we see it often. So that's the question. How do we identify, how are we able to work with this type of data when it's neither consistent, nor complete? Conclusion, right? We talk about results. What some of the work that was presented here, what it actually means for industry, what it meant for service provider within IBM. So this is particular about the eliminating of false positives that exist everywhere. You can see this study actually showed that, when we just started it, and it was confirmed now that it's been a couple of years since we're doing that, 20 to 30% of incident tickets are false positives. So if you think about it, third of the work that support does is not necessary. It will go away all by itself. Right? So that's a big impact. In labor-wise, it might be not much labor. So initially, when we start talking to people, does it take, how long it takes to go to the system, run command, and make sure that everything back on track? And the answer was, it doesn't take me too much, right? It takes 3-5 minutes. So we did some study. It takes 15 minutes, 15 to 20, actually, if we look at statistics, because there's a process in place. A person needs to go to the system, run command, make sure everything okay, obtain proof that it's okay, put it into the system, close the system, close the ticket, right, within the system. So it takes time, maybe not as much as to resolve a ticket, which is real, but it takes a lot of time. So 10 to 15% of labor actually relates to incident management overall. So you can, and 30% of that could be attributed to false positives. So you can see the approximately how big the impact is. And you can hear data from, you can see here data from real accounts. So the first one, is it still? Yes. So here, It is a single account. It is months of data, months of tickets. You can see just applying first level of sort of quarantining the possible false positive provides this benefit. And here you can see, depends on account, what is the monitoring tickets for this account and how many of them false positives were. And you can see the more we monitor, the more false positives, right? But it is, monitoring is the first step in prevention failures and prevention large impact failures. And so nobody will agreed on reducing the monitoring. So the only way to do that and make it smarter, right? Make it better. And I removed number of actually millions here, amount of millions that were saved. But so I don't know if I am allowed to release this information publicly, but you will have to trust me that the impact was significant. So this is false positive. This is a correlation event. So in this talk, we talk about how to get this event to look at correlated events in the sense that maybe by resolving one event, the rest can be resolved, right? So there is a single event, which is your first trigger event, if you wish, and there's a bunch of other events which also come and they all generate tickets. But if you fix the first one, if you fix the root cause, then everything else falls in place. So this is one type of correlation events. And another type is when you, in order to even resolve the system or even to understand a problem that a complex system has, you need to know all the events. So you need to combine them together. An example, you have a system that's running your database, you have application and the application using the database, you have web server, you have application server, all of these distributed systems, and now all of these distributed services. That's where we're moving, and all of them, we need to be able to combine them together in order to say, we understand what the problem is. And so you can see here that, again, if we look at this type of correlation, understanding logs, essentially understanding events, again, we're assuming, we kind of calculated that 30% of the tickets could be also eliminated, right? So again, this is impact of this current work. And finally, maybe where are we going? So, as I said before, the goal is to be able to get information, to produce recommendation, right? To get enough information to produce precise enough recommendation so the recommendation could be executed by the system. And that's true at every level. So what you see here, you can see here overall IT service management a different level. It starts with a solution designer where there is a new application that needs to be deployed. How do I know how to deploy this application? What could be SLA for this or service level agreements for this application? How do I set up monitoring for this application? This is new today. It's all done by people. Technically speaking, we have the data. We can generate the information which is required for solution for this particular application. The next one, service manager. When we run this application, that goes to everything that we talk about. Runtime, how you manage this application. What are you doing with the logs? How you resolve incidents? Maybe how you automate change. All that is in service management. And the next one, service optimizer. This is an idea, a lot of service optimizer, a lot of it done offline. When we look at the data that produced by the services, by the application, and we automatically adjust how the system managed or how the system runs, right? Not by actually adjusting the application, but infrastructure and so on. So this is service optimizer. So all of that, some pieces here and there, right? A lot of work was done before, and some pieces resolve to a certain degree. There are new, in a sense, there are new infrastructure. So we have public-private cloud. We have, of course, legacy system. Now we're working a lot with the services. So it's not, we don't have everything in control. We actually have applications which use mostly external services. How do I understand, without knowing about service enough, how do I understand how to reason about the service point, the integration point? This is new. We also have now more and more applications are stateless applications, and they're sitting in the containers, and they are extremely flexible. So maybe one of the questions that I can ask, well, with containers, I can replace containers seamlessly. So the question is maybe not how to fix, but when is the right time to replace, right? And so on. So new questions, new research, maybe hard research needed. So what logs event analysis can do? And there is just going through what we talk a little bit about, but also what needed to be done. Monitoring systems. Proactive monitoring to detect problem and respond to the events. You can think about dynamic thresholding. Today, there are two types of tools. If you look at monitoring, there are two types of tools on the market. Some are still threshold monitoring, and it's useful, and people like that they have full control of it. Others are monitoring when they get away from threshold, and essentially they look at the patterns of the incoming data and trying to alert based on the identification of a pattern that seems to be leading to some malfunction. So that's also this too. And for some time we were thinking that the threshold base will go away, but it seems to be there seems to be need, right? It's been for a few years, and it looks like they to stay. So both of them require continuous improvement and continuous research. The next one, availability mean time to recovery. So here I see there is how you understand, how you visualize the incident, where it is, and how you can look at the history. Maybe data or history can lead you to understand what the problem is today and how to resolve it. So that's another one. Monitors, right? So this one is goes back to service optimizer, right? Your system is running. Is it run efficiently? Does it give you the best performance ever? Maybe it's even under the sort of, it stays within thresholds, but maybe it can be better. So a system optimization. If we're talking about cloud, there are tools today that to a certain degree can identify underutilization of a system and suggest something to do with it. I haven't seen those that can do it dynamically or can do it with a high confidence, right? So that's another work. Then this last one is the last one, reporting capabilities, right? Of warehousing, and essentially, and it's not as simple as it sounds. You get systems you have an environment which is running on private cloud, on public cloud. It has legacy component to it. You have this piece is monitored by tool X because it's the best tool for your cloud. This piece is monitored by tool Y because that's how it always was done. There is a new application that we just built, and really all we want to do there is to identify tags and pour logs into your system, bringing it all together on the fly. So there are no people who are matching data even at initial stage. It's not simple. It requires a lot of understanding of the data built into the system, right? So we all, when I think at the beginning we were talking about what we start with, we look at the data, we visualize that, and we say, okay, now I know what the problem is. I know where I should go. So now think about it. This first stage needs to be done by your tool, because you take away person from the loop, and the tool needs to be able to bring in information from a new application, new monitoring, and start reasoning about it. So there's many new requirements. This one, looking forward, real-time requirements. Essentially, we're talking about automation. I would like to talk about automation in this case. The closing the loop, bringing events in, creating a ticket, but being able to resolve it automatically. If not, then it goes to practitioner. This one, failure prediction. Still, a lot being done here. There's a lot of analysis of logs and so on. Still a lot to do. Our failure prediction requires, in general, not only ours, but I guess state of the art, requires large number of time series, which we don't necessarily get, right? So how we do that effectively with minimum amount of data? Incorporation domain knowledge with mining results, also not necessarily simple. Integration of different types of information, that's what we talked just a few minutes ago. And from systems to network and devices and services, right? This bringing is as a service. It provides a new set of challenges that we'll need to overcome in the data mining. Before we go there, just two things I would like, two issues I would like to mention, which I think fundamental for us as people who are looking at the data and creating data-driven applications. We need to be able to have to produce confident results using minimum amount of labeled data, right? That's a big. Labeled data exists in very small portions. So the goal number one, be able to work with limited amount of labeled data. And the goal number two, being able to, or maybe to build into the tool interpretations for a person who can look and say, yes, I understand why it's done. Because often it is a black box for people who try to use it. And then there is a very difficult for them to believe into it, right? So that's I think two things that need to be built into the future. This is thanks and acknowledgement of work that was done together with this PhD students, who many of them now working, as you can see, and supported by different funding. If you have any questions, this is email, and the slides will be available at this URL, updated slides. And I think this is thank you.